Good morning. It's an honor to be here in the same room with everyone to share our work, LingAuto. I assume that everyone in this room is at least vaguely familiar with interactive and automated theorem provers. In interactive theorem provers, or ITPs, the user interacts with the ITP to complete the proof. The main job of the ITP is to check the proof written by the user, although most ITPs come with some level of internal automation. In automated theorem provers, or ATPs, the user only needs to specify the problem, and the ATP will conduct an automatic proof search to attempt to find the proof. While the proof search is automatic, for more complicated problems, the ATP might not find the proof in a reasonable amount of time. So, a natural idea is to connect ITPs with ATPs so that when users are writing proofs in ITPs, they only need to provide the major intermediate steps of the proofs, and the ATPs can fill in the details automatically. However, a big problem is that popular ATPs and ITPs use very different logical systems. ITPs such as Coq, Ling, and Agda are based on dependent type theory, while most ATPs are based on first-order logic or higher-order logic. Therefore, we need an interface to translate between the logical systems of ITPs and ATPs. Given a problem in the ITP, the interface should first translate the problem into the ATP's logical system, then invoke the ATP to get a proof of the translated problem, and finally translate the proof back into the ITP's logical system. Our work, LingAuto, is such an interface between the ITP Ling4 and ATPs. There are existing interfaces between other ITPs and ATPs. For example, Isabelle Sledgehammer translates between Isabelle and various ATPs, and Coq-Hammer translates between Coq and various ATPs. Both Isabelle Sledgehammer and Coq-Hammer are hammers, which have additional functionalities like premise selection and might use a portfolio of different proof strategies. We'd like to point out that LingAuto is not a hammer because it does not have premise selection and only supports proof reconstruction of one type of provers. A hammer for Ling4, which uses LingAuto for translation, is currently under development. For those familiar with ITPs, we also want to point out the differences between LingAuto and previous interfaces. LingAuto is different from Isabelle Sledgehammer because Ling4 and Isabelle are based on very different logical systems. LingAuto is also different from Coq-Hammer because Coq-Hammer's translation is based on an encoding of Coq into untyped first-order logic, while LingAuto's translation is based on monomorphization, which we'll get into later. Now, let's talk about the capabilities of LingAuto by looking at some examples. The first example we have is a theorem called snake lemma, coming from abstract algebra. It says that if we have a commutative diagram that looks like this, then we have an exact sequence relating the kernels and co-kernels of the morphisms A, B, and C, and they satisfy additional properties if the morphisms in the diagram satisfy corresponding properties. To formalize the snake lemma in Ling4, we first need to declare the relevant variables, shown here in Ling code. We can see the declaration of objects, the morphisms between the objects, and the premises about them. For simplicity, we only consider the snake lemma for abelian groups, and we only consider the first part of the lemma. Here is what the manual proof looks like. And here is what it looks like if we use LingAuto. We can see that after we've supplied the required premises to LingAuto, LingAuto can prove the theorem automatically. The next example is an equality about real numbers. We want to show that addition distributes over min, using only the most basic method theorems about addition and ordering. This is what the manual proof looks like. And this is what the proof looks like if we use LingAuto. Again, the length of the proof is reduced. In addition to formal mathematics, LingAuto is also potentially useful for software and hardware verification. Currently, LingAuto supports several theories of SMT-lib, including integers, strings, bit vectors, and algebraic data types. Proof reconstruction for SMT solvers can be handled by LingSMT. Now, let's talk about the comparison between LingAuto and previous tools. We found it infeasible to compare LingAuto with tools from other ITPs. Therefore, we only compared LingAuto with existing tools in Ling, including the built-in tactic SIMP and the lightweight automation tool ASOP. We ran all tools on 149,000 out of 177,000 theorems from MATLAB4. Here, some theorems are filtered because our evaluation method is not applicable to them. We gave each tool 10 seconds per problem. We found that LingAuto VBS solves 41.5% of the problems, which is significantly higher than the 19% of SIMP and 32.4% of ESOP. The combined VBS of all the tools solves 53.2% of the problems. On the other hand, LingAuto is significantly slower than existing tools on solved problems. This is potentially caused by LingAuto's verified checker and the frequent definitional equality testing in LingAuto's monomorphization. We'd like to improve these in the future. Now, let's talk about the limitations of LingAuto. To talk about LingAuto's limitations, we first need to talk about the various logical systems used by ATPs and ITPs, starting from first-order logic. In first-order logic, functions cannot take functions as arguments, and quantifiers cannot quantify over functions. In higher-order logic, functions can take functions as arguments, and quantifiers can quantify over functions. If we allow terms to take type as arguments, and allow quantifiers to quantify over types, we get polymorphic higher-order logic. If we further allow types to take types and terms as arguments, we get calculus of constructions. And if we add inductive types to calculus of constructions, we get calculus of inductive constructions. Finally, if we add other nice features such as universe levels, quotient types, and type classes, we get interactive theorem provers. And LingAuto translates from Ling to first-order logic and monomorphic higher-order logic. For problems that are already in the higher-order fragment of Ling, LingAuto can always translate them correctly. If we further allow polymorphism and type classes, we will start to cover many MATLAB theorems. For these problems, LingAuto can usually translate them correctly. For universally quantified type indices, sometimes LingAuto can find the correct instantiations. By universally quantified type indices, we mean variables like the x here, which is quantified and also occurs as the index of the type fin. However, LingAuto cannot handle existentially quantified type indices. Another important feature of Ling4 is inductive types. Currently, LingAuto only has support for certain classes of inductive types, and only when SMT solvers are used as the back-end prover. However, LingAuto will not fail because of the presence of unsupported inductive types. It's just that LingAuto will not automatically generate properties of such inductive types. Users can explicitly supply these properties to LingAuto as a workaround for this limitation. Now, let's get into how LingAuto works. Here is an overview of LingAuto's translation procedure. The translation has two stages, preprocessing and monomorphization. Monomorphization has three substages: quantifier instantiation, lambda arrow star abstraction, and universe lifting. Roughly speaking, preprocessing translates Ling4 into calculus of constructions. Quantifier instantiation instantiates quantifiers that are not allowed in HOL. Lambda arrow star abstraction translates the instantiated formulas into HOL star, and universe lifting translates HOL star to HOL. Here, HOL star stands for higher order logic with universe levels. There is no fundamental difference between HOL star and HOL, and we only included HOL star here for an accurate representation of LingAuto, since LingAuto needs to handle the prevalent universe levels in Ling4. To get a better idea of how LingAuto works, we will look at a simple problem about lists. Two polymorphic functions are involved in this problem. The function C, short for concat, which takes two lists and returns their concatenation, and function M, short for map, which takes a function from alpha to beta and a list of type alpha, and returns a list of type beta. We have two premises about C and M. The first premise, concat soc, says that C is associative, and the second premise, map concat, says that M distributes over C. The result we want to prove is that if we have a function f and three lists u, v, and w, then this equality holds. Note that there are two differences between the left-hand side and the right-hand side. First, on the left-hand side, concatenation is applied first, while on the right-hand side, map F is applied first. Second, on the left-hand side, for the concatenation, it's U and V first, then W, while on the right-hand side, it's V and W first, then U. The proof of this equality is very straightforward. We first rewrite using concat_soc to change the order of concatenation, then apply map concat twice to distribute M over C. Recall that LingAuto wants to translate problems into monomorphic HOL. Therefore, we need to get rid of the polymorphism. First, let's focus on the goal. We can see that, although M itself is polymorphic, M applied to A and B as a whole behaves like a monomorphic function. Similarly, although C is polymorphic, CA and CB behaves like monomorphic functions. Therefore, we can apply the following abstraction to turn the goal from polymorphic HOL to monomorphic HOL. This abstraction will be referred to as lambda arrow star abstraction. Naturally, we would like to apply the same technique to the hypotheses. However, we will immediately find that we cannot because the hypotheses contain quantified dependent arguments. For example, the alpha in concat_soc. Since alpha is quantified, we cannot just turn this C alpha here into an HOL variable. Therefore, we need to first instantiate these quantifiers before we can apply lambda arrow star abstraction. Recall that in the manual proof, we first used concat_soc once, then map concat twice. When we used concat_soc, we are trying to reorder the concatenation of three lists of type A, and the type argument alpha of concat_soc is instantiated with A. Similarly, the type arguments of map concat are instantiated with A and B. We can see a pattern here. When the alpha of concat_soc is instantiated with A, the C alpha here becomes CA, which coincides with the CA in the goal. Similarly, in map concat, the M alpha beta here becomes MAB, which coincides with MAB in the goal. Therefore, these instantiations can be generated by matching applications of the same polymorphic function in different formulas, and this is exactly how LingAuto's quantifier instantiation works. Note that new instances of hypotheses are generated during the matching procedure. Generally speaking, these new instances can participate in a new round of matching and generate additional new instances. Therefore, the quantifier instantiation procedure of LingAuto is a saturation loop which performs multiple rounds of matching. After quantifier instantiation finishes, hypothesis instances that do not contain quantified dependent arguments go through lambda arrow star abstraction. The previous example shows the basic ideas of monomorphization. Similar ideas are already present in Isabelle sledgehammer. The real challenges for LingAuto are the expressive type theory and the various additional features of Ling. Here we list three of them. First, dependent arguments are dynamic in Ling's type theory, which means that whether an argument of a function is a dependent argument depends on how previous arguments are instantiated. LingAuto takes this into account because incorrectly recognizing non-dependent arguments as dependent impacts completeness of the translation procedure. Second, we need to handle Ling's type classes during the translation. Ling 4 uses type classes to represent mathematical operations and mathematical structures. Type classes are not part of standard HOL. Therefore, LingAuto performs type class inference and instantiates type class instance arguments before lambda arrow star abstraction. On a separate note, many type class instances are large Ling 4 terms. Therefore, LingAuto's matching procedure does not look into type class instances. In practice, we find that this has little impact on the completeness of the translation procedure. Finally, LingAuto's translation also handles definitional equality. In Ling 4, two syntactically different terms can be considered equal by Ling's kernel. This is called definitional equality, and LingAuto heuristically detects definitional equality between subterms of the input formulas. In addition to monomorphization, we also want to briefly mention the other components of LingAuto. Preprocessing translates Ling into the calculus of constructions. It translates inductive types when SMT solvers are used as the back-end prover, and handles part of definitional equality. Proof reconstruction of Ling Auto is based on a higher order verified checker which supports inhabitation reasoning and proof by reflection. Currently, it only supports the native prover duper. Proof reconstruction for SMT solvers can be handled by Ling SMT. Finally, we would like to briefly mention issues of Ling Auto and future plans. One of the most critical potential improvements is implementing a better monomorphization procedure for Ling Auto. The current version of Ling Auto cannot deal with existentially quantified type indices, non-leading universal quantifiers, and does not fully respect Ling force definitional equality. Having a better monomorphization procedure will enable more problems to be translated correctly. Another issue is the HOL to FOL translation. Ling Auto have a rudimentary translation procedure to send problems to SMT solvers. However, if the problem is not already in FOL after Ling Auto's translation, Ling Auto will fail. Of course, apart from these two, there are also other important potential improvements, such as improving the performance of monomorphization and the verified checker, and implementing support for mathematical structures in MATLib 4 that are not declared when Ling Auto is being compiled. Alright, that's all for today's presentation, and feel free to ask questions. Since I'm sleeping far away in California right now, Professor Barrett will take care of the Q&A section. Thanks for listening.